we're going to continue our journey through the regions. The effect, or chem regions. So the effect of a catalyst on a chemical reaction is to provide a new reaction pathway that results in a different what. So hopefully you remember that this kind of little chart right over here. So remember that, let's say on the y-axis is potential energy, and let's say on the x-axis we're going to have reaction progress. Reaction progress. Now, in order for a reaction to occur, it's sort of like pushing a ball up the hill. It has to encounter a little obstacle, right? So a reaction might look something like this, all right? So essentially, right, this line right over here, this flat line over here, represents the potential energy of the reactants. And that makes sense, right? This is the potential energy when you're starting out, right? When you're starting out, the potential energy is going to be this much right over here. Potential energy of the reactant. Now, in order for some not all reactions, chemical reactions, are something known as spontaneous, right? Not all chemical reactions just like happen naturally. A lot of them require some amount of energy for it to occur. This energy is known as the activation energy. It's basically the difference between sort of a highest point on this sort of hill thing you're looking at and the potential energy of your reactant. All right, your potential energy of the reactant has to overcome this energy barrier in order for the reaction to start. Top of this hill, it's known as the transition state or the activated complex. It's basically when your thing starts to do its thing and react. All right, now, think about like a match, right? If you're lighting a match on fire, in order for that to happen, in order for that chemical reaction to happen, you have to scrape the match on the match box, right? You have this match box right over here with its little dot thingy. You have like a little match. In order for the match to light on fire, you have to scrape the match on the match box, which provides the initial boost of energy for this reaction to occur, aka the light thingy gets on fire. All right, I cannot talk today. But anyways, what a catalyst does, it basically lowers the activation energy. So notice how the potential energy of your reactant and the products is still the same, but essentially what you have done is you've lowered the activation energy. So now it takes less energy for it to happen. So it lowers the potential energy, not the potential energy of the reactant. The potential energy of reactant and products stay the same, but it lowers the activation energy. Lower energy. This one is just the second law of thermodynamics. This one you guys kind of have to memorize. Systems in nature tend to go towards lower energy. Think about this is why sort of heat spreads, right? Heat, a lot of thermal energy, right? If you have something really hot, let's say a boiling pot of water, right? That's very hot. So what the heat will do, what that thermal energy will do, is from all this hotness, quote unquote, it's going to spread around to the surroundings, and that way the energy will lower. However, from the heat that spreads, right, other stuff is going to happen. For example, if you have like ice cube on the table, you have all these ice cubes, let's say around this boiling of pot of water, what's going to start to happen? All the ice cubes are going to start to melt, and that increases the entropy. Entropy is just a kind of measure of disorder. And if you have a solid, right, a solid piece of ice will have this sort of like crystal structure to it. It's very organized. But if you take a look at a liquid, that's going to be less organized, right? It's going to be the molecules of water are just going to be shifting around each other. It's going to be less organized, right? Because the intermolecular forces are weaker. And gases have even higher entropy than liquids. Gases are even more entropy than liquids because gases just go everywhere, right? There's no attraction between the particles, or not much intermolecular attraction between the particles. So all the gas particles are just going to be flying everywhere. So yeah, the atoms of which element bonds to each other in chains, rings, and networks. This one you just kind of have to memorize that this is going to be carbon. Remember that network covalent bond? I'm pretty sure there was like a question before that talked about like the allotropes of carbon in this exact Regents, and you remember that hopefully if y'all don't remember this, remember that network covalent. It's basically like you know what a covalent compound is, right? One thing is bonded to this other thing, right? Covalently, quote unquote. Now a covalent network is basically when it's sort of like you have this network, right? It's this network. There's many sort of these covalent bonds happening with one another. So It's basically like this sort of long chain. It should kind of remind you of a crystal lattice of an ionic compound. It's sort of like that. All right. The reason why carbon is able to form networks is because it's able to have 4 bonds, right? Because carbon has 4 valence electrons, so it's able to form 4 bonds. That makes it great for a network. It also forms rings, and yeah, that's kind of all you have to know. Ethene. This one is just all reference guide. Ethene, see this ENE at the end? This means that this is something known as an alkene. And alkenes follow the formula. It literally gives it to you. Ethene. CnH2n. It literally gives you the diagram as well, right? Because ethene, there's a double bond between the carbon. So what happens is that this double bond means that there's going to be twice the amount of hydrogens as there are carbons, right? See in this diagram, this double bond, for each carbon there's going to be 2 hydrogen bonded to it. So yeah, ethene, that's going to be CnH2n. All right, this one's just 3, because F, you gain an electron, that's going to yield this ion, this fluoride ion. All right, so yeah, that's because electrons are negatively charged. So if you gain an electron, you're gaining a negative charge. What substance is in Arrhenius base? Remember that Arrhenius bases, when you dissolve them in water, that's going to release hydroxide ions. So, once again, if you do not know this, common bases, you have calcium hydroxide. Yeah. Because when you dissolve this in water, this is going to have the calcium ion. This is also going to have 2 hydroxide ions, right? And yeah, that releases hydroxide ions, which means it's an Arrhenius base. Remember Arrhenius acid, that releases H+ ions, but Arrhenius bases, they release hydroxide ions. 2 light nuclei, that's just gonna be fusion, bruh. It's like two things combining into a heavier nucleus. That's just gonna be nuclear fusion. If you did not know that, does the reference guide have it? I don't know, actually. Does it have it? I honestly don't know if it has it or not. Is there an example of a fusion reaction here? Nah, I don't think so. Oh yeah, I don't think so. But you could just kind of like remember that, nuclear fission, you kind of break things apart. But fusion, it's like it's a name, right? You're fusing kind of 2 things together. Fission, you're breaking this apart. Specifically, uranium-235 is the example, right? Used in nuclear power plants. All right. Using equal masses of reactant, the relative amount of energy released during a chemical reaction and a nuclear reaction. All right, the nuclear reaction is just going to release way more. Freaking uranium is used in atomic bombs. That's all I have to say. All right. Let's see. The ratio of the mass of, oh man, you have like a couple of like isotopes. You have to know what they do. In the Regents. This is one of the annoying isotopes. So diagnose thyroid disorders. I'm pretty sure that's iodine 131. Right. A lot of things, a lot of isotopes, they can be useful because when they decay, then they can do certain types of stuff. So I'm pretty sure dating geologic formations. Actually, number 4. I'm pretty sure this is carbon-14 dating. Carbon-14 dating, right? When carbon-14 decays, it can be used because the ratio, there's going to be like, you're measuring like the ratio between carbon-14 and I'm pretty sure nitrogen. So then what happens is I'm pretty sure you kind of like measure like the ratios, right? The remaining amount of carbon that's remained in that organic sample, and you can actually determine the age of organic materials or once living things that have died. And you just kind of have to remember that uranium, this is what U-238 does. When it kind of decays, you can measure out like the ratio between these two, and it's used to date kind of rocks, geological formations. Yeah. So yeah, that's just like an annoying thing you got to do. All right. Bright light spectra. and a mixture of at least 2 elements is shown below. Which elements are present in the mixture? So what you have to know is that kind of each element has its unique individual sort of bright like spectra. All right, and this spectra is produced from, remember how if you have like a nucleus, right, and you have these electron shells around it, remember that when an electron goes from a higher shell to a lower shell, it releases energy as light. Now, there's different wavelengths of light. Basically, different kind of types of visible light. Obviously, you have the colors, right? You have red, orange, green, yellow, blue, purple, right? You have all these different colors, and all these different colors are determined by different wavelengths of light. So not every type of light is the same. Now, each element got its individual thing, right? Individual spectra. Now, for the mixture, all you have to kind of do is you kind of have to line things up. So notice how for G, it lines up with what's in the mixture, right? Everything in G lines up with what's happening in the mixture, and everything in L lines up with what's happening in the mixture. So this is going to be a mixture of G and L, right? Because both of them are in the mixture, right? Both of them are in. So you just have to line up the lines. Neutron of chlorine in an excited state. So remember that basically when atom gets excited, what that essentially means is that one of the electrons in the atom moves up into a higher energy level. So let's take a look. So for chlorine, the electron configuration for chlorine is 287. All right, 287, meaning that there's 2 electrons in the first shell, 8 electrons in the second shell, and 7 electrons in the third shell. Now, imagine if one of the electrons from the second shell moves up into the third shell. So you're going to have 7 electrons in the second shell and then 8 electrons in the third shell, right? So 1 electron basically moved up into a higher energy level. Well, that looks like answer choice 4. The amount of electrons you have has to be equal, right? When an atom is in an excited state, that does not mean that it gained any electron. So answer choice number 1 just doesn't make sense because we have a different amount of electron than we started with, right? And so does number 3. That also doesn't make sense. Yeah, let's continue. Student measures mass and volume density based on, what is the percent error? Based on table S. All right, let's go to table S actually, and then we'll see. All right. So table S, this one is just they just want you to use a periodic table. So I'm going to use the periodic table. All right, where's my aluminum at? All right, don't know why it took me that long. All right, aluminum, density of 2.7. So it has a density of 2.7. And you measured it out to be 2.85 grams per cubic centimeter. Now, if you do not know the percent error formula, well, they are, luckily, pretty sure they give it to you, no? They don't give it to you. Wow. Oh yeah, percent error. Never mind, bro. I knew. All right, the percent error is the measured value minus accepted value divided by accepted value. I knew they had that. I was just, all right. So it's going to be, all right, so it's going to be your measured value, which is, in this case, 2.87, minus the accepted value divided by accepted value. Or you can think about it as new minus old divided by old, right? New value minus the original value divided by original value. This one you just have to put into the calculator. You remember, multiply this by 100 because it's percent, right? It's a percent, so it's out of 100. And it's going to be approximately 5.6%. Magnesium and calcium have similar because they're because the atoms in the ground state. All right, so basically, once again, things in the same group share similar chemical properties because notice how they have the same amount of valence electrons, which is just the outermost electrons. So because they have the same amount of valence electrons, outermost electrons, well, that's going to lead them to have similar chemical properties. So they're going to have magnesium, calcium, Mg and Ca. Well, they both have 2 valence electrons in the outermost shell. That's what it's going to lead them. I'm sorry, I'm doing a lot of scrolling around. The periodic table. Which property generally decreases? It says elements of period 2 of the periodic table are considered left to right. What generally decreases? All right. If we look at period 2 is just going to be basically a row, right? It's a row in a periodic table. A group in a periodic table is basically a column. A row in a periodic table is called a period. Now, as you go from left to right in a period, what actually happens is that the atom gets smaller. Because what's going to happen is, let's say if we were looking at an atom of lithium. Lithium has 2 electrons in the first shell and 1 electron in the valence shell. Okay, that's fine. But the thing about lithium is that it only has 3 protons. It has 3 protons. Now, if we take a look at it and compare to beryllium, well, beryllium has 4 protons. So what's actually going to happen is that beryllium is going to be smaller, a little bit smaller than lithium, because this 4 plus charge, right? This 4 proton charge is going to be stronger than this 3 proton charge. So then what's going to happen is, remember that opposites attract each other, right? So positive gets attracted to negative. So this protons, because there's more of them, they're going to attract the electrons a little bit more, right? They're going to pull it a little bit closer to the nucleus, so it's going to be a little bit smaller. So as you go from left to right in the periodic table, generally your atomic radius decreases. The balance equation for a reaction of butane. Well, this is basically saying that if we have 5 moles of butane and this reacts with oxygen, let's just say we have enough oxygen for this reaction to go to completion, how many moles of CO2 is going to be produced? Now, there's actually something known as a mole ratio. So basically, the coefficients of your chemical reaction, they don't have to represent like molecules. So you can think about this reaction as 2 molecules of butane react with 13 molecules of O2 to form 8 molecules of CO2 and 10 molecules of water. But it can also be 2 moles, right? You can also think about it as 2 moles of C2H4, and remember that a mole just represents 6.02 times 10 to the 23rd of something. This number is very big because remember that atoms are very small. So if I want to count the amount of atoms in, like, let's say, I don't even know, like a Rubik's Cube or something, that's going to be like a little too much. So I'm just going to use moles as my unit because it's a very big amount. So I'm going to need like a unit that represents a very large amount of atoms, right? So I can say that for my mole ratio, imagine if I have 5 moles of butane and I originally started out with 2. Now I want to find out the amount of carbon dioxide I have, given that my original amount, right? The original amount that was produced is 8. So essentially what I'm doing is I'm doing a ratio where this is essentially nu minus old divided equals nu minus old divided by old. Essentially what I'm doing is my new amount divided by the original amount that I had, that's going to be equal to the new amount of the other thing divided by the original old amount I have. So in this case, right, the new amount of butane that I have is 5 moles, and I originally had 2. Now I want to see how much kind of new carbon dioxide is produced, given that the original amount is 8. And then, then I could solve it here. But if you just kind of use a calculator, you could just see that this is going to be 20. Right? And that kind of makes sense because, I mean, if I want to get from 2 to 5 right over here, I have to multiply this by 2.5. Right? So notice how I have 2.5 times the amount of reactants that I had originally. And that means that I'm going to form 2.5 times the amount of products that I have. Right? So this is just going to be 20. Right? X is going to be equal to 20. Percent composition. Remember that percent composition is just going to be part over whole, right? It's going to be mass of part over mass of whole times 100. So in this case, we're given that the gram formula mass for N2H4 is going to be 32 grams per mole. Now, what is the percent composition of mass of nitrogen? So this is basically saying if the total thing weighs 32 grams for every 1 mole, well, how much of the weight is made up of nitrogen, essentially, right? How much does nitrogen contribute to the weight of N2H4? Nitrogen has a molar mass. If you look at the periodic table, nitrogen has a molar mass of around 14 grams per mole. So if we have 14 grams of nitrogen, right, that's going to be the same as 1 mole of nitrogen, right? 1 mole of nitrogen weighs 14 grams. Now, because we have 2 nitrogens here, we have to multiply this 14 by 2. So essentially, our nitrogen right over here weighs 28 grams. Now we have 32 grams in total, right? We have 32 grams per mole in total. And this nitrogen weighs 28 grams per mole. 28 grams per mole. So if we divide these two things together and multiply by 100, we're going to get 87.5% on our calculator, which is around 88%. And all of this just means that nitrogen accounts for 88% of the weight in N2H4. It makes up 88% of the weight in N2H4. That's all that means, right? And if nitrogen makes up 88% of the weight, that means that hydrogen has to make up 12% of the weight, right? Because it has to add up to 100%. Which ion in the ground state has the same electron configuration as an atom of neon? All right. So remember that neon has an electron configuration of 2A, meaning that there's 2 electrons in the first shell and 8 electrons in the second shell. Now let's take a look at these answer choices. Ca2+. So imagine if we have calcium, and this 2+ just represents that it lost 2 electrons. So imagine if we start out with calcium and it lost 2 electrons. Now the electron configuration is 2AA. And that's not the same as neon, right? Neon, it's just 2. Neon, the electron configuration is 2A. But the electron configuration of Ca2+ is just 2AA. 2AA. There's an extra A at the end, so it's not correct. Sorry for all this scrolling around. What about Cl-? No, Cl-. Cl is right here. Cl- just means that a chlorine atom has gained an electron, right? That's why it has a negative sign. Because if you're gaining electrons, you're becoming more negative because electrons are negatively charged. So chlorine originally has an electron configuration of 2A7. But because it gained 1 electron, it's going to become 2A8, which is completely different from neon. So it can't be that. Let's take a look at lithium plus. No, lithium originally has an electron configuration of 2,1. Lithium, the lithium ion, right? That just kind of means that this plus sign means that you're losing electrons, right? If gaining electrons makes you more negative, losing electrons makes you more positive. And because there's this plus sign at the top, lithium has lost an electron, 1 electron, and then it becomes basically the same electron configuration as helium, but that's not what we want. So the answer has to be O2-, right? Imagine if you have oxygen. Oxygen has electron configuration of 2,6. Now, what about the oxygen 2+? What about O2? 2-, sorry. Well, what's going to happen is it's basically going to be the same electron configuration as the original oxygen, except that you gained 2 electrons. So imagine if it's the same electron configuration as this oxygen right over here, except you gain 2 electrons. So 6 plus 2 gives you 8. And 2A is the same thing as neon. So yeah. All right. Let's continue. What compound has the strongest intermolecular forces? So the higher the boiling point, the stronger the intermolecular forces. So that's just going to be HF. All right. Because think about it, right? If your compound has a strong intermolecular forces just represent kind of the attractions between molecules. So look, the actual chemical bonds, right? The covalent bonds, whatever, ionic bonds, there's something known as intramolecular forces. Molecular forces. Because it's inside a molecule. It's kind of what's keeping the molecule together, right, in the first place. Intermolecular forces are attractions between different molecules. So it's not the same molecule, it's different. It's different molecules. It's intermolecular forces. It's in between, right? Different molecules. Now, the stronger these forces are, well, the more heat it will take in order to break, or not break, but weaken these attractions, right? Because in order for something to boil, think about water boiling, right? The attraction between the water molecules have to be broken, or some, I don't know why I keep saying broken. The attractions between the water molecules have to be weakened so much to the point where it can actually escape from each other's grasps, right? It can just flow out freely. However, if the attractions were not that strong, it would have a lower boiling point. It would take less heat in order to weaken the attraction. So as boiling point increases, that basically just means that as your intermolecular forces, the strength of these increases, your boiling point increases. xenon STP. Xenon STP. So what do we have here? Well, xenon is a gas at STP, and STP basically just means essentially standard pressure and standard temperature. So standard temperature is 273 degrees Kelvin or 0 degrees Celsius. So STP, that's 0 degrees Celsius, and then that's going to be about 1 atm for the pressure, right? The pressure is 1 atm. Now, standard STP, remember that Kelvin, remember that actually 273 gives you Kelvin. Remember that for temperature, if you add 273 to the degrees Celsius, you get the temperature in Kelvin, right? So this is how to convert from Celsius to Kelvin, right? They're both ways to measure temperature, but for Kelvin, you just add 273 to it. So if I want to convert from 0 degrees Celsius to Kelvin, this would just be 270 degrees Kelvin. Now, if you go to your reference guide, notice how for neon, the boiling point is 23 degrees Kelvin. So at 273 degrees Kelvin, this thing would already be in the gas phase, right? It would be past its boiling point. It would be in its gas phase. So yeah. It would not be answer choice number 2 because remember that xenon is a noble gas. Noble gases rarely react. So yeah, it's not going to really react with anything. It's not going to react with itself, right? This is showing that an atom xenon reacts with itself. Nah, that ain't how it works. Or what is the amount of heat when the temperature of water increases? This is basically Q is equal to MCAP, MC delta T. So we're trying to find the amount of heat absorbed when the temperature of 75 degrees of water increases from that to that. So once again, we are going to use our reference guide to help us solve this problem. We're going to scroll all the way up. Notice how the heat capacity of water is 4.18, and you can do joules per gram per degree Celsius. So this is saying that in order for me to raise, so this right over here is basically saying, in order for me to raise 1 gram of water by 1 degree Celsius, it would take this much energy for me to do that, 4.18 joules of energy for me to do that. Now, what I'm going to do is we have M right over here stands for basically our mass, right? C right over here represents our specific heat capacity, which is this thing I'm talking about, right? And then delta T represents our change in temperature. So our change in temperature is going to be 15 degrees Celsius. And we have 75 grams. Notice how when I multiply everything out together, all of this cancels out, so you're just going to be left with joules. Joules is a measure of energy. It's a unit for energy. So it makes sense that we're left with just joules, right? And multiply this together, we're going to get about 4,700. All right. Fastest. Reacts at the fastest rate with this. Okay. This should be answer choice number 4. You should know the things that increase the rate of the reaction. Right, rate of reaction, this kind of just represents, to put it simply, how fast the reaction goes, right? And you can actually do stuff to speed up the reaction. So one thing you could do is you could just increase the concentration of whatever you have. If you add more of the stuff, it's going to react, right? To simply put, if A reacts to form B, if you add more A, you're going to form more B, right? Increase HCl, concentration of HCl, you're going to get more stuff forming, right? It's going to be at a faster rate. And higher temperature, increasing the temperature would also increase rate of reaction. Also increased rate of reaction. This is because at a higher temperature, more particles are going to collide, right? Remember that in order for a reaction to occur, and this is something known as collision theory, but essentially, in order for a reaction to occur, first of all, the things got to hit each other, right? If the things don't hit, it ain't going to react. Second of all, it has to collide in the right orientation, has to hit each other in the right way. And finally, it has to hit each other with enough energy. Remember I was talking about the activation energy before? So yeah. So collision theory states that in order for a reaction to occur, all these 3 things have to happen. Now, if I increase the temperature, not only is that increasing the amount of collisions there are, but it's also increasing, I mean, if the particles are traveling at more speed, that's just going to increase like the energy, right? It's going to increase the force that they hit the other thing with, and therefore it makes it more likely that it's going to react. So yeah, given that the system represents a reaction at equilibrium, which statement describes the concentration of two gases in the equilibrium? Must be constant. All right, so what you have to know is that at equilibrium, the concentrations of both the reactants and the products, they're going to be constant, okay? And this is because at equilibrium, the rate of both reactions are going to be the same. So rate of forward reaction equals the rate of reverse reaction. So let's say if I have this example right over here, let's say if I have it in a container. So let's say if the blue thing represents N2O4, and let's say if the green things represent 2NO2. Notice how, actually, let's just do this, yeah. Okay. Now, you guys might be thinking, okay, the concentration of N2O4 must be less than the concentration of NO2. But the thing is that that's not actually always the case. In fact, at equilibrium, depending on, there's other external factors, like, this is just simply because, it doesn't have to be in the correct ratio because of different sort of conditions. For example, remember that volume and pressure affects the concentrations, right? If you decrease the volume of the container, right? If you have a container that's very small, well, what's going to happen is that the reaction is going to shift to the side with decreased pressure. So imagine if I have this reaction at equilibrium, and what I do is I place this in a smaller container. Place all of this in a smaller container. Well, originally the pressure, let's just call that P1. This is the original pressure. However, now what has happened is that because the container has gotten smaller, well, the pressure of the second container is going to be greater than the pressure of the first container because the container is smaller. So the particles are going to hit the wall more often. So in order to restore equilibrium in the pressure, the reaction is going to shift to the side with the least amount of gas particles, because the less gas particles you have, less pressure. So it's going to shift to this side, and it's going to shift to the side with the least amount of moles of gas particles. In this case, the reactant side has the least amount of gas particles, so it's going to shift to that side. So the concentrations of the reactants and the products at equilibrium, a lot of times they're often not reflected by the stoichiometric or mole ratios, right? A lot of times they are not represented by the ratios because there's just too many external factors to put into account. And you can just remember Le Chatelier's principle for that. But the concentrations have to be constant because the rate of the forward reaction is equal to the rate of the reverse reaction. So if both the forward reaction and the reverse reaction are happening at the same rate, right? Well, then the concentrations are going to be constant the whole time. You wouldn't like really see a change in the concentrations of things. Speaking of Le Chatelier's principle, we have this reaction at equilibrium. What change will cause the equilibrium to shift to the right? So we want the reaction to shift to the right. So how can we do this? Let's see, increasing pressure, increasing the temperature. It has to be increasing the temperature, no? Because if you increase the temperature, what that essentially does is you're increasing the amount of energy there is, right? If you treat energy as a reactant, you're increasing the amount of energy there are. So that's going to, increasing the concentration of a reactant is going to shift the reaction to the right? Because you're going to form more products with that more energy, right? So yeah. And everything else shifts the reaction the opposite way. For example, if you add more products, that's going to shift the reaction to the left. Or if you increase the pressure, right, the system is going to find a way to decrease that pressure. And in order to decrease the pressure, reaction is going to shift to the side of the least amount of gas particles. So it's none of these. Adding a catalyst only changes the activation energy. It doesn't shift the equilibrium to the right. Now that it just kind of it just like provides an alternative pathway for a reaction, and it increases the rate of the reaction, but that doesn't shift it to the right. When you add a catalyst for a reaction, what that essentially does is it increases the rate of the reaction on both sides. So it kind of like balances out, if you know what I mean. All right. a chemical name for this is going to be what? All right, I'm just going to be focusing on this N, H, and then this C right over here. I'm going to be focusing on that. All right, because guess what? On our periodic table, we have. All right, this is propylene. All right, so go back to example here. What we essentially have is we have N, and that's kind of linked up to two different things. Now, if we go to the periodic table, you can see that. Notice how for amines, notice how we have N, and it's combined with three different things. Where this R right over here basically represents the carbon chain, right? So notice how this N's link up to two different things, and then you have this R right over here, which just represents a carbon chain. So in this case, right over here, this is 1-propa-amine. The reason why it's called that is because prop, basically, once again, your periodic table kind of carries everything, but or your reference guide, but prop represents 3. All right, so this is 1-propa-amine because we have 3 carbons, right? We have these 3 carbons in a chain, and this 1 essentially comes from the fact that our amine is located at carbon 1. So yeah, that's pretty much it. So we already know that it's amine, so I mean, answer choice number 3, I mean, you don't even have to know how to name it. You just see that this is an amine, and like, you know, amines have an amine ending to it, so it's going to be amine. Yeah. All right, next question. Sorry guys, my thing crashed, but anyways, given the formula for a compound, this compound is classified as a what? Notice how there's a triple bond here. What the triple bond tells you is that this is an alkyne. If you do not know this, once again, you got the reference guide. Notice how for alkynes, you have a triple bond. So yeah, if you have a double bond, that's alkene. Single bond, that's alkane. Fermentation. So for fermentation, what you're essentially doing, fermentation, you probably heard of fermentation before, right? Like you're fermenting, like, I don't know, like soybeans, fermenting. Pretty sure you can ferment. Can you like ferment pickles or something? I don't even know. All right, but anyways, for fermentation, the thing that kind of gives it away is that you start out with sugar. All right, and what's going to happen is you're going to create alcohol, or ethanol to be specific. So ethanol, right? Because it's alcohol. So yeah, and this is going to be plus carbon dioxide. So the only answer choice is number 3 because it starts all with sugar. Hopefully by biology class, you memorized the formula for sugar, C6H12O6. I mean, for fermentation, you could also think about just like wine, right? You're taking the sugar and it's turning into like the alcohol, right? So yeah. Oxidation number of copper changes from what? So oxidation number, it's basically represented by these little like numbers at the top, right? You kind of see all these little numbers at the top. So chlorine usually forms a -1 charge, all right? Chlorine usually forms a -1 charge. So chlorine has a -1 charge. Now, there's 2 chlorines in total, right? So it's going to have a -2 charge in total. So a chlorine, this CO2 right over here is a -2 charge. Now, notice how the entire compound right over here is neutral, meaning that the charges have to add up to 0. So Cu has to have a 2+ charge because 2 minus 2 gives me 0. It's neutral, right? It's neutral. Now, notice how copper is by itself, right? After the copper has done its reaction, it's done its thing, what essentially happens is that the copper is just by itself. And when you have just an element by itself, it's going to have a charge of 0, right? It's neutral, right? So in this case, copper has gone from 2+ to 0. Given the reaction representing a reversible reaction, according to one acid-base theory, the 2 H+ donors are what? Given the equation. What are the 2 H+ donors in here? So this reaction basically goes both ways. So this right over here turns into this. So what happened here? It looks like what has happened is you have this C3 whatever blah 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 if you don't know anything. But what happens is it looks like it has given up an H+ ion. All right. So this thing right over here has given up an H+ ion. So remember that when you have water and that accepts an H+ ion, that's going to form hydronium, which is H3O+, right? notice how the charge is the same on both sides, right? There's both a plus charge on both sides, and notice how there's on both sides there's both hydrogen, there's both 3 hydrogens and 1 oxygen, right? So balance of charge and balance of mass. Now, so this right over here is something known as Bronsted-Lowry acid. It's all about protons, all right? So Bronsted-Lowry acids, what that basically does is it donates a proton. And a proton is also known as an H+ ion. Because a regular hydrogen atom has one proton, and 1 electron. Now, in H+ ion, what basically happens is that you have lost an electron, right? Losing electrons makes you more positive because electrons are negatively charged. So if you lost this 1 electron, now you're just going to be left with a positive charge, aka 1 proton, aka an H+ ion. Now, the thing is that there's something known as a conjugate acid and a conjugate base. So basically the base is the thing that accepted. Bases, Bronsted-Lowry bases, are things that accept protons, right? Accept protons. Now, when a base accepts a proton, it becomes a conjugate acid. Conjugate acid. It basically becomes an acid because it can donate that proton back, right? The base has gained a proton. So what it can do is it can donate that proton back, and it basically became acid, right? So the base kind of becomes acid after it accepts it, and then the acid kind of becomes the base after it donates it. So the 2 acids we have here are this thing and H3O+. All right. Which spontaneous decay? Which reaction represents a spontaneous decay? This should be. Is this on? No, it's not on. All right. Spontaneous decay. All right, but basically, elements that I'm pretty sure have atomic. When elements go through alpha decay. So alpha decay. Something known as alpha decay. Elements go through alpha decay when their atomic number is greater than what was it? Pretty sure it's 83. So when the element's atomic number is greater than 83, it'll just naturally go through alpha decay because just the nucleus is a little too big. So answer choice 1 shows that, well, it's spontaneous because atomic number is greater than 86, so it goes through alpha decay. And once again, this was the reference guide I'm saying, but basically it releases an alpha particle or a helium nucleus, right? And the alpha particle is from alpha decay. Notice how this helium right over here matches up with this helium right over here. So, you can kind of sort of, I don't know, figure a way through that, even if you don't exactly know it.